everyone, and welcome back. Before we get started, there's something about our last episode that I would like to discuss. In the last video in this series, we created a velocity versus time graph following the motion of a person moving from left to right, and that person was speeding up. It was the last problem we did. Now, one of the things that was discussed was the slope of the line of that graph. And the slope of the line of that graph is what I termed the rate of change of velocity. Now, that concept, the rate of change of velocity, is the single most important concept in this course. And you're going to hear me state that a number of times throughout this series. You will constantly be assessed in a first-year physics course on how quickly is the velocity changing, what direction is it changing in, and what brings us to this particular video, why is it changing? So, with no further ado, let's begin our discussion on forces. To start with, the very concept of a force is so fundamental in physics that creating a definition for it actually isn't very easy. You could find a definition or two in the dictionary, but we are going to start, since it's a very basic concept, with a very basic definition. Here is how we are going to define forces. Force, an interaction between two objects. That is it. That is our definition. So we're going to build from there. Now, let's talk about the units for force to start us out. The SI unit for force in a physics course is called the Newton. No prizes for guessing who it's named after. Now, in the United States, the most common unit for force is actually the pound. People in America typically use this for their weight, how much the earth is pulling on them downward. But if you were to push against the wall and to say, I'm pushing against the wall with 5 pounds of force, that is a perfectly acceptable statement. Just so we have a comparison between the two, 1 Newton is equivalent to 0.225 pounds, and 1 pound is equivalent to 4.448 newtons. So a shorthand version is a Newton is almost a quarter of a pound if you would like to do some quick mental math to have an idea of how much force you're dealing with in a physics course. So when you are dealing with forces in a physics course, one of the important things to think about is how to recognize and define your force. So let's talk force designations. Most of our force designations are going to use the following pattern. Capital F, first symbol, comma, second symbol. F means force, obviously. A, in this case, represents what object is causing the force, and B represents what object the force is being exerted on. This is the object we are tracking. In physics, in the beginning for a first-year physics course, you are tracking one object at a time. So you will typically have a goal to find out how many forces are on your target, what direction those forces are in, and how much magnitude those forces have. In that respect, let's start talking force diagrams. Force diagrams are probably the single most important visual representation in a physics course. The concept is very simple. It is a picture representing all forces exerted on an object. It represents their directions and their magnitudes and what causes the force. To show you a few examples, in this case, I have block A resting on block B. Block B is sitting on a table, and they are not moving. If we were to do a force diagram of block B is pushing up on block A, and the Earth, which is an object, is pulling down on block A. Now, if you notice, these two forces are equal and in opposite directions. So, using vector addition, these two forces will cancel, which means this block is not moving and it's not going to move anytime soon. If we were to do a force diagram block B, we have the green vector on the bottom, which is from Earth pulling downward, the red vector, which is exerted downward from block A, pushing downward on block B, and we have a blue vector pushing upward from the table. Now, if you'll notice, the blue vector is the same size as both the red vector plus the green vector, which means in this case, all three of these forces cancel, which means the blue vector is the same size as the red and green combined. In other words, your combined force for both of these is 0, which is a key point we're going to discuss in a little bit. In this case on the right, I have another block. Earth is pulling downward again. We have the surface or the plane pushing perpendicular to the surface on the block, and we have another force from the surface pushing up the ramp here. Now, if this block will assume is stationary again, which means this is a frictional force here, preventing this from sliding down. Frictional forces are going to be in discussions a little later. And a side note, they designate a N here, and there's a reason for that, which we're going to discuss very soon as well. So one of the primary goals in creating a force diagram is typically to find what is called the net force. The net force is the combination of all forces on an object, also known as the resultant force. Resultant is a term also used in vector addition, which is exactly what this is. So let's step aside for a minute and let me show you an example of finding the net force on an object and talk about a few other terms along the way. Now, to demonstrate a force diagram, we are going to use this object. I have a statue, it is on a base, and this is the ground. And we're going to have a little man pushing the statue to the right. The first thing you're going to want to do is decide where you're going to place your force diagram, and there's really two choices here. Typically, you will do your force diagram right on your target object. In this case, the statue is going to be my target object. I'll place a little circle dead center of this object. Traditionally, it should be approximately where the center of mass of the object is. Sometimes you're asked to draw a force diagram away from the picture, which is also okay because there is more space. Now, the first force that we're going to put in a force diagram is from the planet itself. And due to our designation, we're going to call this force Earth on statue. So I just have this abbreviated. You can write out the full words like we saw earlier, or you can put a legend on the side if who's ever looking at it is not going to be sure what you're talking about. The second force we're going to put in this diagram is going to be from the ground, upward. This is force ground perpendicular on statue. So the Earth is pulling downward on the statue, but the statue obviously is not falling downward. In fact, it's not moving downward or upward. It's not changing velocity in either of these directions. So the ground is pushing up with the exact same amount of force that the Earth is pulling down, and I represent that by the arrows being the same length. The perpendicular symbol is due to the fact that any surface will produce a force perpendicular to itself. Next is going to be a force from the person. So I have force person on statue, and that force is to the right. And lastly, I'm going to have force ground parallel on statue, and that is the force that is going to be to the left. And that is a frictional force between the ground and the statue. So a very quick demonstration. Let's say force Earth is 300 newtons. Well, the ground is going to be pushing straight up with the exact same amount of force because we've already established that this object is not moving upward or downward, also 300 newtons. Let's say the person is pushing with 200 newtons, and the parallel frictional force on the ground is 180 newtons. So looking at this, calculating net force actually is pretty simple here. Looking at the y-axis, my force upward and force downward would cancel completely, so there is no net force on the y-axis. However, on the x-axis, I have 200 newtons to the right and 180 newtons to the left, so F net would be 20 newtons to the right. And you can recognize this directionally with the positive negative signs. But a really good way to really show you recognize the direction of that force is to literally draw an arrow. Now, at this point, I would like to mention two things. Number one, force diagrams only contain forces. You do not put anything else in a force diagram. You do not put velocities, do not put displacements, do not put anything else in a force diagram. Two, the net force does not belong in the force diagram either. The net force should always be displayed somewhere on the side because you will be using it later to find other things about the motion of the object. While we are here, there are two more things I would like to mention, and they concern these two forces from the ground. Now, earlier, we went over the proper naming nomenclature for forces. Force, the object exerting the force, and your target. However, these two forces from the ground can get a little confusing, especially if you're a beginner. So there are names for these two that break the rules a little bit that anyone grading your assessments should recognize pretty easily. The first one is this force perpendicular from the ground. Force ground perpendicular is also often called force normal. The symbol typically is F capital N. So this perpendicular force from a surface, and that is a side note about this force normal force, it consists of a perpendicular force from any surface, not just the ground. This can be the horizontal ground, it can be a ramp at an incline, or it can be a wall that would push this way and a ramp would push perpendicular this way. So either or. The other one that will often have its own name that will kind of break our rules a little bit is this force ground parallel, which is just simply called force friction, symbol FF. So the ground produces two forces, one perpendicular and one parallel. They are typically broken down into two nicknames, force normal for the perpendicular and force friction for the parallel. However, something to keep in mind, if you were ever asked the question, what is the combined force from the ground on this object, that combined force is neither up nor left, it is both upward and to the left. You would literally have to combine these two forces using vector addition. That would be two-dimensional vector addition, which is going to be a later video. So for now, this is a very simple example of your basic force diagram and proper naming nomenclature. I hope you have found this video useful. This is Mr. M signing off.